So, hello and welcome from me as well about my presentation about airtightness testing of high-rise buildings. Today, I will talk about the adventures, the challenges, and the lessons that we learned from 4 tests. 3 in Vienna. This is a triple tower that you can see here, by the way. You can see the pointer, I think. Can you see the pointer? Oh, doesn't matter. That you can see here, the triple buildings in Vienna and one building from Luxembourg. The tests were done in 2021. All buildings, all buildings have a height between 108 meter and 125 meter. This is very high comparing to the Statue of Liberty in America with 93 meter and the Red Rock Lange Anna on the island in Germany where I lived. At this point, I would like to say thank you. Thank you for the testing team in Vienna to give us the possibility to test high-rise buildings. These are Emanuel, Johannes, and Thomas. Thank you also very much to Gary Nelson and Colin Olson from America, who supported the tests online. This is me on the island, and I would also like to thank you all the people in the background that maybe not be visible for you. This is Sören Peper and Wolfgang Hasper and colleagues from the Passivhaus Institute. This is the colleagues from the University in Vienna. These are also my colleagues from the BlowerDoor GmbH. And today, of course, thank you very much to Maria for the organization of this webinar and take care of us as a presenter. And thank you very much for Nolan, Valerie, and Benedict that you helped to improve and develop a test procedure for high-rise buildings. Thank you for that. So I wish you and me some fun in the next minutes. What I will show you today is the test objects and the requirements that they have, our challenges, needs, and worries that we have before and during the test, idea of the setup of the test equipment, lessons that we learned and the test results, and I will give a summary at the end. The test objects and requirements. You see here the 4 buildings in Vienna, the triple tower and 1 tower in Luxembourg. The height is, as I told, between 108 and 125 meter, between 31 and 36 floors, and an internal volume of the triple tower around 70,000 cubic meter, and the tower in Luxembourg is a bit larger with 104,000 cubic meter. And you see here the building envelope around 17,000 square meter, and 25,000 square meter building envelope of the building in Luxembourg. The requirements. In Austria, we have had the requirement of the N50. The building should be less than 1.5 air changes per hour at 50 Pascal. And in Luxembourg, we have a very high requirement. The permeability over the building envelope should be less than 0.9 cubic meter per hour in square meter. The QE50 is, in my eyes, a very fair value, and it shows the quality of the building envelope. So I converted the 1.5 air changes per hour also for the building in Austria to the permeability, and should be less than 6.6 cubic meter per hour in square meter. 7 times more than the building in Luxembourg. What are our challenges? So is it possible to measure high-rise building, as Valerie explained us before? We don't know. What is our motivation to do this kind of test? We would like to reduce the leakages in the building envelope. We want to learn more about how to test tall buildings, because we think the ISO 9972 is developed for small buildings, but not for high-rise building. In example, the 5 Pascal limit for the baseline pressure or natural pressure difference, how to calculate the lowest test point, and how to achieve a uniform induced building pressure in the entire building. Valerie will talk a bit more about this later. Our motivation was to get results and share the results and our experience with you in order to develop a test procedure that gives us repeatable and reliable test results also for high-rise buildings. And we thought, what is the best location for the fans? Should we install all the fans on the ground floor? Or is it better to install the fan on the upper floors? We would like to have a single zone building so that we can test the entire building. And is it possible to create a uniform induced pressure over the entire building height? Or do we have a pressure drop, or as Valerie said, pressure loss over the building heights because of narrow stairways and lift shafts? How can we detect an uneven pressure or the pressure loss? What are the reasons for this kind of pressure drop, and what can we do if we see this kind of pressure drop? And we were very nervous about the weather conditions. We can make the test setup and plan it and do it, but we cannot control the weather. Our worry was that the thermal lift can cause high natural pressure differences. And I will show you our first tower that we test. You make an estimation before, some days before we did the test. There's a formula I will show you. With the building height and the expected temperature inside and outside of the building, you can measure, you can calculate, estimate the pressure, the baseline pressure of the building. And for this building, under this condition, we will expect a baseline pressure of minus 54 Pascal on the ground floor and plus 54 Pascal on the top floor. This is too big in my eyes, too large, too high. But with this estimation, we can say to the customer, please reduce the inside temperature, turn off the heating several days before we do the test, or to move the date, the test date. Another worry is the wind. What does the wind with high-rise buildings? Which pressure differences can we expect at the bottom and at the top, on the windward side, on the leeward side? We don't know. So our idea was to test it, to measure it. So I will show you now the main idea of the test setup. We got help from the Passive House Institute. They developed a baseline, and now we get help also from Nolan and Valerie, who write a paper from the AIVC about high-rise building airtightness test. Thank you for that. What we want to do. So I talk first about the pressure test points we would like to take from building envelope between inside and outside of the building. We took pressure differences between inside and outside on the ground floor, between 1 and 4 sides of the building, north, east, south to west, if possible. Or yeah. Why do we want to do this? We want to calculate with these values the leakage graph using the average. If we take more than one pressure difference, the average of all sides of the building from this level. We want to see the natural building pressure at the bottom of the building in real life in order to ensure that each test point during the multi-point test is negative for the depressurization test and positive during the pressurization test. And we put several test points at the top of the building. We measure 1 to 4 pressure differences between inside and outside, all 4 sides of the building. Why do we do that? Also, we want to see here the real natural pressure difference because of the stack effect and because of the wind at the top of the building. And the same as before, we want to have a negative pressure during the depressurization test and a positive pressure in the entire building during the pressurization test. Here you have an example of the Triple Tower 1. We tested it on the ground floor and on the top floor. We put in pressure gauges in order to measure the pressure difference between inside and outside on all 4 sides of the building. And here you see how it looks like on the building side. Here you see a small wind T on the outside of the window, and the hose run through the window using a capillary tube, and the other end of the hose, and see here on the pressure device, and you can compare the side and the outside in order to get the pressure difference. We was thinking about the fan location, so it was a leaky building with a high air expected leakage rate. So we planned fans on the ground floor, and we also planned fans on the upper floor if we have a pressure loss over the building height. What we also do, and what today I really can recommend, is to measure the internal pressure difference inside of the building at 2 points inside of the building. Here, for example, between the ground floor and the top floor, because you can see if there is a pressure loss because of a narrow staircase or another obstacle. You can see the pressure loss. And our wish was in all this building that the pressure drop or loss within the building is less than 10% of the induced building pressure. The induced building pressure is the pressure that is created only by the fans, by the measuring fans. Here's the example of Tower 1. We measured more building pressures between the upper floor and the lower floor, and all the difference where we have fans, and also to the basement, in order to take care to have a uniform pressure distribution over the entire building of the induced pressure. For that, we cannot do it. We needed industrial climbers to help us, because you see here all the hoses and cables that we put up in the building in order to get all the information down to the building, and we need brave people who are doing this for us, the installation. Oh yes, here's a view over Vienna. So in the end, we get test results, and hopefully also reliable test results. Here they are. The triple tower get an air change rate around 1, and the building number 4, the building in Luxembourg, has an air change rate from 0.2, a very low air change rate. In my eyes, a better value to compare the quality is the QE50, the permeability of the building envelope. You get around 4 cubic meter per hour and square meter for the triple tower, and 0.9 for the building in Luxembourg. In order to get an impression of the high of the airflow, it's around 75,000 cubic meter per hour, deep pressure or under pressure or over pressure for the triple tower, and around 23,000 cubic meter for the building in Luxembourg. It's much tighter, much tighter. Even it is bigger, it's much tighter. So this is the view at night over Vienna from the triple tower. What have we learned? We have learned that it is very important to have a station, we call it base camp or location, where all cable, tubes, information come together. We called it base camp, and you can see here base camp. Most important is the kitchen cooking place in order to get something to eat. The test takes around 3 days. Here you have the location of the test fans. We have an open place, and from this open place, the air can go to each door that is connected to a lift shaft or to a staircase. And here you see the central control of everything. It's at one point, and one person is saying, turn off the fan here and on there, or check a tube here and there. So the number and position of the fans, depending, one criteria is the quality of the air barrier. If we have, let's say, a high QE50, a leaky building, we need fans also on higher floors in order to get the uniform pressure distribution over the high. If we have a building with a very good air tightness, it's okay to place the fans on the ground floor, and we need 5 to 6 fans for this building and between 12 and 15 fans for the triple towers. Another important point are the passes, the airflow passes that we have in the building. So we need vertical air. So we want to test it as a single zone building. So we need vertical air passes in the entire building so that the air can come down to the test equipment and from the leakage to the vertical airflow passes. And we need large, big openings in this vertical airflow passes. There it is. That the air can flow through the fans to the test equipment. Here I have an example of a stairwell in the triple tower, and an example of a stairwell in the tower in Luxembourg. The difference is we have a wall between these two stairways, and this makes the channel where the air can go up and down much smaller than in Luxembourg. And because of this, we need fans on higher floors as well. It's a second point why we do this. And because we have 2 wide and open staircases in Luxembourg, we can put all the fans on the ground floor level. In the triple tower, it was necessary to add 1 more shaft, and you have a look into the lift shaft, 100 meters high, to have another vertical pass. And we opened several doors in this lift shaft in order to get the air also in the horizontal part of the buildings, in the floors. Here you see a setup of the fans in the outside of the building, so in the building envelope, and we need a large open place corridor so that the air can flow from the fans to the staircases and to the lift shaft. All the fans also in the upper floors were installed in building envelope, in a door or window in the building envelope. So what do we see as a real natural pressure differences caused by wind and differences in temperature? I take the building with the most information that we get. It's on the border that we can test, in my eyes. It's a tower number 3. We had wind in 3 before that time, and a difference in temperature between inside and outside of 17 degrees. This causes on the ground floor -10 Pascal under pressure. At the top floor, plus 66 Pascal over pressure. 66 Pascal over pressure. You know, we do normally a test up to 50 Pascal, 60 Pascal in our multi-point test. So this is the baseline pressure, the natural pressure. No fans are running. What we learned is the temperature difference and the building height and the distribution of the leakages over the building cause the level of baseline pressure at the top of the building and at the bottom of the building. And wind generates fluctuation, less fluctuation on the ground floor, a bit more on the top floor. Here you see again the triple tower with 66 Pascal on all 3 sides of the building, and on the ground floor on 3 sides on the building we have -10 Pascal. The difference in temperature is plus 70 degrees, and we have high baseline pressures at the top That's the bottom of the building. In summertime, inside temperature is larger than outside temperature. This is also interesting to see. In summertime, we have only 4 degrees between inside and outside. And in this case, the outside temperature was higher. It was warmer outside. So we get a bit under pressure at the top of the building, the opposite side than here, and a bit over pressure on the ground floor. But the values, you see, the values are much more less than lower than at the first building. Also, the Triple Tower 1 and the tower in Luxembourg with difference in temperature of 3 or plus 7 degree generate higher pressure differences, yes, but these 3 buildings we could easily test, and it was much more. I feel much better with the test results here than with this building. It's on the border. What we see, the smaller the temperature difference between inside and outside is, the lower is the baseline pressure on the ground floor and on the top floor. What is the impact of the natural pressure difference to lowest test point of the multi-point test? I take also the building with the extreme building pressures, tower number 3. The baseline pressure on the ground floor and on the top floor form the lowest test point for the multi-point test. In order to have a negative pressure during the depressurization test, we have to shift this pressure difference by 66 Pascal in order to have a negative pressure. So we have to compensate this. And we can start with 76 Pascal minus and the buffer. For the overpressure test, so in my eyes too high, and for the overpressure test, we can start with 0 Pascal plus a buffer. This is, at this point, I would like to refer to Valerie and Benedict. Benedict will explain you the buffer, and Valerie can explain much better than me how to create the test point for this lowest test point for the test. My recommendation is, if you have a building around 100 meters, the temperature between inside and outside shall be less than 12.5 degrees. In other words, less or equal than 1,250 meter Kelvin. I think this is, I can handle this difference in temperature and that high. What is the effect of the leakage distribution over the building height? You can see it here. So, we can explain it with a natural pressure plane. This is the point where we have 0 Pascal at the building envelope. And what we see, it is the natural pressure plane is not located in the middle of the building. It's somewhere else. And it's an indicator if you have a natural pressure plane in the lower part of the floor. We have here more leakages in the lower part of the building. If we have the natural pressure plane a bit more at the top of the building, we have more leakages at the top of the building, on the upper part of the building. What do the wind do in the question of fluctuation? We see a lower fluctuation on the ground floor than on the top floor. So the size of the pressure fluctuation increases on higher floors. My recommendation is to install the fans on the ground floor level so that they see less pressure fluctuation. You can control the fans better and you get more stable results. Only test that wind less or equal to 3/4. We make experience that are okay in my eyes, and increase the test time per test point, for example, to 60 to 100 seconds in order to get a larger average time. What is the impact of the wind direction streams onto the building? Here you see again the natural pressure differences, the baseline pressure differences on 4 sides of the building on the ground floor. Here you see on the top floor also 4 pressure differences. And what we see here is that the fluctuation, the up and downs, are higher at the top of the building, and that the pressures are higher on the windward side of the building. So in this case, my recommendation is, if it is possible, install the test equipment, the fans, not on the windward side of the building. What do we do if we see a pressure drop or pressure loss over the building high? For example, in one building, we turn on the fans, and we could create only 35 Pascal induced pressure at the bottom of the building and get only 30 Pascal induced pressure at the top of the building. The pressure drop, the pressure loss was too high. What can we do? We set a fan or turn on fans in the critical zone, let's say in this case at the top of the building. And then you can compensate pressure loss over the building high, and it's fine, it's okay. So something more about the manpower, woman power, and more. Here's a testing team from Vienna and here from Luxembourg. We need time to do this kind of airtightness tests, and we start with airtightness tests in the buildings in Vienna, and the buildings in Vienna were leaky. So this is our experience from, let's say, the leakier building. We have had several online meetings before we do the test to plan the equipment and how to put on everything. My colleagues did several visits on the construction site. They make pre-tests in apartments in order to get an overview, a feeling of the building envelope. And in the end, we needed 3 days to carry out this test, and the nights, of course. The first day, more or less, doing the setup. The second day, searching for leakages, closing doors. The multi-point test over and under pressure itself takes, let's say, around 1 hour per test, 1 hour per test, so 2 to 3 hours maximum. The rest of the 3 days are set up. Do the setup, and on the third day to take down the test equipment. Some interesting information maybe for you. It was good to make a construction visit on the construction site because we needed 1,200 timber wedges to fix the self-closing doors in the open position. And we stopped the time for triple tower number 1. One person needed 7 hours to open all the inner doors and the stairways and to check if all windows are closed. 7 hours, 1 day, that's 1 working day. It is a challenge to close all openings and check all openings in a big building, in a high-rise building. And we see building elements like this humidity-controlled element in the building envelope. It takes time to discuss before, and it takes time at the building site what to do with this kind of elements. Do they open at a certain building pressure, or do they keep closed? Should we seal it or not seal it? This is time consuming, but I think you know it because it's more or less the same as you have for testing big buildings. Now I will come to the end. In my eyes, airtightness tests of high-rise buildings are possible. A good airtightness is easier to do the job, to do the airtightness test. If you have a good airtightness of the building envelope, and if you have large airflow passes, it's also easier to test. We need additional test points on the ground floor and on the top floor in order to get an overview of the building pressure differences between inside and outside and control the fans in order to do the test in the way Valerie will explain you later. It's in order to get the uniform induced pressure check the pressure drop or loss inside of the building. If you have a pressure drop, install fans in the critical zone and turn them on to compensate it. With wind less or equal than 3/4, we make good experience, and the temperature difference between inside and outside should be around 10 Kelvin at a building that is 125 meter high, or in other words, less or equal than 1,250 meter. Then it becomes more difficult. But if you have this condition, it's fine. It's okay. You can do it. Also, in my eyes, very important is, in order to compensate the uneven pressure distribution due to the wind impact and the impact of the thermal lift, do both pressurization and depressurization and take the average value in order to calculate more with this average. This is it from me. I hope you have had some fun, and thank you for your attention. And questions will be collected by Valerie later, because I have to leave now.